All right, and now we're back to take a look at the last of the major units or lessons that we've got in Unit 8 on fluid mechanics. This one is geared around the idea of the continuity equation. Now, it's actually kind of independent of some of the other materials that we've looked at least for the depth that we're going to look into. That being said, there were a number of lessons earlier, like on Bernoulli's equation, that I wanted to look up previous AP not multiple choice, but free response questions, but parts of those would often have continuity equation built into them. So while this is going to be something that we're not going to be talking a whole lot about the pressure that we've been talking about for the last couple of lessons, this is something that combines with that in a pretty regular way, especially on the questions that are asked. And also, the driving mechanisms behind it are somewhat similar, like it is related to all of those things, but it's an important thing to understand to round out our introductory understanding of fluid mechanics. Okay, what the continuity equation does broadly is it applies flow rates, and conservation properties. In this case, we also saw that Bernoulli's equation applied a conservation property or a conservation idea onto fluids in conservation of energy. In this case, continuity equation, I say conservation properties because the most common way that this is described is either conservation, cons, of volume, which is what we're going to be looking at directly, or mass, which more fundamentally is actually what we're seeing. In this case, I'm going to take one extra step on this and I'm going to point out that the continuity equation is actually applying conservation of mass, or matter, if you would prefer, onto fluid flow. Now, when you track it down to what we're going to be looking at, that is the fundamental basis for this idea of continuity equation. In short, however much water I put into one side of the pipe has to equal how much water comes out the other side of the pipe. Or technically you might have like a storage container or something in there in real life, and that's where the continuity equation and other materials can get a bit more complex at the higher levels. We're going to, once again, look at incompressible flow rates, and we're going to be looking at non-storing systems. Basically, the flow rate in equals the flow rate out. This is an introductory level for higher level classes that you will see, where you may have systems in which your flow rate in might not necessarily equal your flow rate out. In this case, continuity equation is very similar to, at least for electric circuits for AP2 and APC E&M, your next step in study, to Kirchhoff's junction rule, where that one's conservation of charge, but basically what comes in must be equal to what goes out of a given point. So I am tracking down that the continuity equation at its core is actually an application of conservation of mass, and therefore it must be true so long as we actually meet the limitations that we've got for the form we are giving you on continuity equation. I do like to give the fundamental backgrounds on these so we can actually see that as we go forward and learn all these subtle little things in different units of study, that there are a lot of core ideas and concepts that most of these actually track back to that are the fundamental foundation for our scientific understanding. In this case, I'm going to go ahead and give us the equation as it shows on the equation sheet so that we've got that. It is area 1 times speed 1 is equal to area 2 times speed 2. Now in this case, we've got area star is going to be the cross-sectional area. Basically, size of pipe. And it's not always like a pipe or anything like that, but pipes are what I end up going to in this because for me, fluid mechanics has so much practical application in the idea of plumbing, and that's where a lot of people would end up applying it. So I think of fluid flow, water flowing through a pipe. So area is going to be our cross-sectional area. So if you had a pipe, grab this, imagine that this was longer and a pipe. Cross-sectional area is where you cut it in half. That's a cross-section. And then the area is the part that you would see. So for a lot of ours, it's actually going to be a circular area, or they might give you a rectangular area. But circular areas are going to be very common because pipes are usually round for a variety of reasons. V star In this case, please note, I'm not putting the little lines on the top, so this is a lowercase v. This is the speed of the fluid. Okay, now real quick, looking at our units on this, we've got speed in meters per second, and then we've got a cross-sectional area, which would preferentially be measured in meters squared. Now, you may be given the diameter or the radius of the pipe in centimeters or some other value, but remember, for us to work through, we want to try and put SI in order to get SI out. I will say this, if you are using just the continuity equation by itself, whatever units you put in are the same units that you will get out. So you could actually have area in centimeters squared and speed in whatever units, say meters per second, and you will get out, as long as you've got meters per second over here, centimeters squared. So you might get it where it works even if you're not using the correct units, but I would caution you to be aware of that. In this case, whatever units you put into this equation, you will get back out, but you can only rely on that for equations like this because you have A and A, V and V. You can't just say, oh, I don't have to use SI units and I can put any units in and I'll just get those same units out. That isn't something that applies broadly. So if you had A1, V1 equals something else, as we will see in just a moment as I walk through what this is actually saying and how it connects to conservation of mass, then you might run into more problems. And in some of the questions, the AP exam has actually asked you about the volume flow rate, which we'll see at least in some of the sample questions or some other ones that are coming up. But real quick, let me show you what we've actually got. Let's look at our units. So we have that this thing, I'm going to put question mark, is equal to A1V1. We're saying that when I multiply these, I get a constant number that I can then apply to another spot in the fluid flow, just like we did with Bernoulli's equation. And we said that that was conservation of energy, that we were basically finding the energy per unit volume, technically, but at one point, and then therefore we could compare that to the energy of another point in the same flow. Well, this is the same thing. We don't know what this thing is, so let's see if we can get insight into it by looking at our units. Our area would be preferentially in meters squared, and our our velocity, our speed, would be in meters per second. Now, I keep using velocity and speed interchangeably. In this case, we are actually, I believe, using the speed for this equation. Technically, you can also do this as a dot product between the area vector and the velocity vector. That is not something that we're looking into for the scope of this class, but might have applications later on. But it would be the speed, how fast the fluid is flowing at the given spot where you have the area. But let's look at our units. Whatever this thing is, it has units of meters cubed divided by seconds. Well, those are weird units, but let's think about what we would have. What units, what thing would have units of meters cubed? Well, hopefully you're saying that's volume. And here's where the capital V comes in. How much space you have. Divided by, well, what's measured in seconds? A time. So this is a volume divided by a time. And at least one of the grading rubrics that I've seen, they actually made reference to trying to do this, although they had it as a weird squiggly V. Volume divided by time is a variable that I might, or an expression that I might use in this because we're talking about our volumetric flow rate. And I want to pause here for just a moment because if you actually look at any modern applications of, say, plumbing technology, if you go and get a new shower head, as I have done a couple of times because the places that I've moved in just kind of have a regular shower head and I like some of the fancy ones with the little handles and whatnot so that I can maintain my luxurious hair. But one of the things that you look at is it describes how much water it actually uses, and it would say gallons per minute is usually the measurement that they have. Gallon is a unit of volume in the imperial system, and minute is a unit of time. Volume per time is actually a pretty common thing to use, especially for plumbing systems, because it describes how much water you're actually moving. And therefore, if you have, say, for instance, a water heater that holds, I don't know, something like 20 gallons, well, that means if you're using 1 gallon per minute, then you can only run hot water for 20 minutes before you run out of hot water in your tank and have to wait a while it heats up more. So that's one of the ways where it becomes a really applicable day-to-day thing, is thinking about fluid flow in terms of volume per time. And we see that here in the continuity equation. So while we'll be asking you a specific set of focused questions, there's a lot more that we can actually do with this. More to the point, Okay, volume per time, this is coming up with the idea of conservation of volume, functionally. Basically, if I put 1 gallon in one side of my pipe, well, in the time that it takes for me to squish 1 gallon in, that's got to push through all the stuff, and it's got to push out 1 gallon's worth of water on the other side. That's the idea. So you could say conservation of volume, because our volume would be a conserved quantity. So whatever I push in on one side, that equal amount has to come out the other side, and that is the basis for the continuity equation. But that actually relies entirely on incompressible flow. Now, once again, this is a topic that we're using and assuming for our studies here at the introductory level, but as you go to the later levels, water isn't just generally seen as compressible because you need insane pressures to even compress it a little bit. So water is usually pretty reliably incompressible. However, if you go into things like aerospace engineering, which is some of my background, then you may find that if you're dealing with air, say air flowing through a ventilation system, air handling units. Air is something that is much easier to compress, and so you might not necessarily get this equation to apply to it properly, especially if your fluid can be squished. Because then I could take something where I put in a certain amount on one side and not the same amount comes out the other side. That doesn't happen because somewhere in there we've squished one part of it. So this continuity equation assumes incompressible flow. If you try and apply it to a system where you do have compressibility, well, then that equation may not hold and likely won't. Okay, because we have incompressible flow, what we're actually saying is this, finishing up this little tangent that we've got, but giving you a deeper understanding and a view of things to come. On top of that, both my exam and the AP exam like to ask you when you apply these ideas, what's the fundamental principle of physics that this is based off of? We said that it was conservation of mass or matter, because that's a thing that outside of nuclear reactions we can't create or destroy. So in this case, I've got a volume divided by time, but remember we're also dealing with a density that I could multiply that by. So I would have density times volume divided by time, and I would end up with density times volume is another way of writing the mass divided by time. Which brings us to the last notation that I'm going to introduce on here. And this is more for some of my materials that I may make reference to. I don't expect these to show up on the AP exam, but on some of the questions I've seen them not be surprised and write the grading rubric to say, we kind of expect students to see something similar to this, but they could call it whatever they want. We have a volume flow rate, which is volume per time. Another way to write that in the standard notation with calculus aspects is V dot. Whenever you have something that has a dot over it, it means the rate of change with respect to time. It actually means the time derivative as a simplified notation, but usually when you have this, a value that's changing over time, you could put a dot above it and that would give you the same thing. So in this case, this is a volume flow rate. It's looking at how much volume goes through in a given time, again, gallons per minute. We also have a mass flow rate. This is a very common one, m dot, which is mass flow rate. And the other reason that I'm covering this is it wouldn't surprise me if in the future they actually start bringing in the mass flow rate. When I went through my fluid mechanics classes and even introductory studies, we would actually look at that as the preferred value, and we could then begin dealing with compressible flow as well. Kilogram per second. Oh, I guess up here I could do meters cubed per second, or you could have things like gallons per minute or cubic feet per second. If you look around, a lot of these things dealing with fluid flow, either in air handling systems, ventilation systems, or particularly with plumbing, they'll a lot of times use the top one. Air systems might actually go with something closer to this. And then the last one that I'm going to bring up that you don't necessarily need for this unit, but you might see in the future is heat, Q divided by time. Heat transfer rate is often written as Q dot, which is a heat transfer rate. That's an equation that we actually learn in AP2, so you might be seeing it next year. This would be in joules per second, aka watts. Okay, now that we've got some of that, I've got a few things that I want us to look at in applying these ideas, hopefully in ways that will help ground them for you. The first is a conceptual way of describing it, something that you can imagine, and for me, it has always worked really well with the continuity equation to understand how it functions. But we basically have let's go with garden hose. Now, this is a thing that a lot of people end up playing around with when they're younger. Let's see, so let's go with, we've got some ground here, a person, possibly me, and then, why do I keep doing that? I've got a garden hose that comes along like this, and I'm holding the hose, and then it has water shooting out like this. And I just kind of point it, and the water comes out and then goes down, much similar to the demo we saw towards the end of our last lesson with Bernoulli's, although it wasn't because of the height of the water, but because of the pressure that's built up in our plumbing system. But one of the things that you would use, especially when I was younger, or if I wanted to get the water to go farther, is you would take your thumb and you would cover part of the hose. So for instance, let's look at this from the hose viewpoint. We've got part of the hose here, and then we end up with the cap on the hose. And then we've got water flowing through like this. And then it goes out the hose. Let's say originally, without me putting my thumb on it, the water flow rate through all of this is V1, and I will call that, let's say, I could do an experiment, we're not going to, but I could do an experiment where I hold it, it goes out, I can measure how far it goes horizontally and the height that we're at, and I could do projectile motion, work backwards, and actually find what its launch speed is. That's an important skill to have, because I could see questions like that being on the AP exam, or my exam, or your introductory physics exam. But let's say that I did all of that and I found that it was moving at, I don't know, 4 meters per second. So we've got the following. Let's say that the area of my hose is here, and it is based on the radius of the hose here. So let's say that this is a radius of r, which results in an area 1 of, let's see, pi big R squared. Now here's what I'm going to do. I'm going to come in and I'm going to take my thumb and I'm going to block, let's say, half of the flow here, which means I can no longer have water flowing out this way. But on this side of the hose, I'm still putting in a certain amount of water. In fact, what is my flow rate? Well, my flow rate, I could say the following. My flow rate at this point in the hose is going to be A1 V1, and that would be equal to my volume flow rate, how much I've got coming into that part of the hose and basically coming into the hose at all. Well, in this case, I would have pi r squared times 4 meters per second equals my V dot, which is my flow rate. I'll clean that up a little bit. This board is a little weird. I'm still getting used to it. Now, I could go through and I could take full measurements. We could do the full math on that, but that's going to be a little bit of a pain. I'm going to have basically that my flow rate is therefore equal to 4 meters per second times pi r squared. Okay, let's say that my thumb comes in and now blocks such that I've covered half of the area. Now, that means that I've covered more than 1 r or something like that. So what I'm going to say is A2 is going to be equal to 1/2 pi big R squared, where this is my original area, and now I'm blocking half of it, so I've got half of that. So coming down, I've got the following. V dot after, at the point of my thumb, basically, is going to be equal to V2 times my area, I guess writing it in order, A2 times V2. Area 2, I just said, is 1/2 pi big R squared. Now, if we gave you the radius instead of the area, you would have to do a little bit more math. But I've got half of the area, because I've blocked half of it now, and then we've got V2. Well, whatever's coming into the hose on one side has to be equal to the amount coming out of the hose and flying through the air on the other side. So I could say that this is 4 pi r squared equals 1/2 pi r squared V2. And then I solve for V2. Now my pi r squareds will actually cancel out. I can divide both sides by that. I multiply 2 on both sides, and I would end up with the following: 8 meters per second equals V2. So if I cover half of the area, the water comes out twice as fast, and that's why it starts going much farther and hitting with a little bit more force, for want of a better term. Why does it have more force? Well, it's going at a higher speed and therefore has more dynamic pressure, and then that pressure being applied over to an area, that sort of thing. So it combines a lot of our previous topics all together. Well, this is basically what the continuity equation sets up. Now, this is applied in a bunch of places too. There are a lot of faucets that have it where the pipe that comes in is much larger than the actual opening to the air. You'll see a lot of them where they kind of funnel down to more of a point so that they end up having a higher speed out of the faucet, giving you more water pressure. It hits a little bit harder, that sort of thing, has higher dynamic pressure, but you end up with less water, arguably, overall. With a bunch of those shower heads that I mentioned, you can kind of increase the water pressure, but usually doing so might decrease the water flow rate. You have it at a higher pressure, but you end up with not as much water as you did before. So a lot of times it's a balancing act. All right, last thing that I want to bring up is we're going to take a look at the first couple of parts of an old AP-B question from the 2009 exam. I think this was the second set, Form B, that they had. But it's a sprinkler system. I'm going to walk us through the first few parts of this because these come directly from AP and will also give us actual numerical values for us to work with. And then I'll talk over briefly how you could apply our previous lessons on Bernoulli's equation to solve the others. Okay, an underground pipe carries water of density 1,000 kilogram per cubic meter to a fountain at ground level as shown above. At point A, right down here, which is 0.5 meters below the ground, the pipe has a cross-sectional area of 1 times 10 to the -4th meters squared. Remember, when we're dealing with meters cubed and meters squared, that's actually a really big value. So if you're dealing with a regular pipe, you're actually going to be dealing with a very small number, which is what we see here. At ground level, the pipe has a cross-sectional area of 0.5 times 10 to the -4th squared meters. The water leaves the pipe at point B at a speed of 8.2 meters per second. So we got 8.2 meters per second right there. Calculate the speed of the water in the pipe at point A. So with this, we could go through and we could try and apply things like Bernoulli's equation, but on this, we've actually got our limiting factor is going to be continuity equation. Because if I've got 1 cubic meter of water flowing past point A in 1 minute, the same amount of water must be going past point B. In short, this is the hose question that we just talked about, except built into an AP question. So the first thing that we need to apply actually is the continuity equation. So 2009B, we've got the following. Part A, we want to apply our continuity equation. The cross-sectional area at A times VA will be the cross-sectional area at B times VB. Now, the cross-sectional area at A, they tell us, at point A, the pipe has a cross-sectional area of 1.0 times 10 to the -4th meters. So this is 1.0 times 10 to the -4th squared meters. And we are told that it goes, we don't know the speed at that. We want to know VA. That's going to be equal to our cross-sectional area at point B, which they say is 0.5 times 10 to the -4th meters squared. Now you may be thinking, why didn't they just make it 5 times 10 to the -5th? Well, they're doing this so you can actually see, hey, at a quick glance, what happened to our area? It used to be 1, now it's a half. We actually cut our area in half. Well, based on our last sample, when we cut our area in half, we end up doubling the speed. And if we were to cut our area down to 1/10 what it was before, we would have 10 times the speed. There's a proportionality in there because of this relatively simple equation. But we've got that it actually exits the pipe at, I believe it said 8.2 meters per second. So let's go ahead and double check our numbers. But we could multiply all of this out. But when I solve for this, go ahead and do that, VA, I believe we will come up with 4.1 meters per second. The reason why is our areas, this area is twice that, so I could divide this over and we would end up with 2VA equals 8.2. We divide both sides by 2 and we should end up with 4.1. Let's take a look. On this question, here's the grading rubric. 3 points. 1 point for a meaningful use of a correct expression for the flow rate, AV. In other words, an attempt to substitute the volume for volume and speed. So basically they're saying, hey, we're applying continuity equation. 1 point for relating the flow rates at point A and B, actually straight up writing it out with that connection. And then finally, 1 point for the correct answer. Hey, look at that, 4.1 meters per second. So that's an example of where we would encounter continuity equation, at least on a previous exam. I want to build this up and connect it to previous lessons, but feel free to move forward and actually check a bunch of samples in continuity equation. But it's mainly area at 1 point times the speed at 1 point equals area at another point times the speed at another point, because we deal pretty much exclusively with incompressible flow. All right, B, calculate the absolute water pressure in the pipe at point A. And so this was not old terminology, it's proper terminology, but terminology that was emphasized on the old APB exam. In this case, what you would do is you would set up the following. The pressure at A plus rho G HA plus 1/2 rho VA squared equals PB plus rho G HB plus 1/2 rho VB squared. Now, I'm not going to solve this full thing. Yeah, I don't know if it's my parallax or if it's the board or what, but V squared, whatever. Okay, we would set up Bernoulli's equation. Let's go through and fill in some of the key ideas. We know rho is 1,000, G is 10, basically. And so the key things that we would need, we now know that VA, the speed at point A, where that was A larger? Yes. So A, this one was 4.1 meters per second. This one was 8.2 meters per second. Our height at point B, going from a reference point, let's make down the lowest point along A, 0. So we would be at a height of 0.5 is what we would put in here, and a height of 0 for this one. Now, the last thing, and one of the reasons I wanted to talk about this was, what we're actually looking for is this. This is our absolute pressure, or our pressure in the pipe at that point, is what we're looking for. In this case, PB, here is where you need to think about the things that we've talked about. The point here at B is open to the atmosphere, and I believe they tell us that the atmospheric pressure, they might not actually, but in the grading rubric they definitely list it. So this value is actually 101,300 pascals because it's open to air. That's why I want to make certain that you see a few examples of this in our lesson so that you're cognizant of and thinking about, okay, what pressures I need to put where. So we've got that. Taking a look at the solution on this. This one is worth 5 points, or on the original old APB exam, the total question was worth 15 points. So this was about a third of the work that they wanted you to do. 1 point for applying Bernoulli's equation. 1 point for using atmospheric pressure at point B. See, that's worth a point. 1 point for correctly substituting in the other things. And then finally, 1 point for a correct... it says, let's see, for correctly substituting values. Basically, this is one of the ones where they say if you got some of the numbers wrong, as long as you get an answer consistent with the values you had before, you get this point. It's basically a point for the correct answer. But if you forget to actually include atmospheric pressure, you don't get burned twice. You just miss out on 1 point. And here's a good example of 1 point for correct units for the answer. Now on the modern exam, anytime you give a numerical answer, you need to put the correct units on it. There's a good bet that you will not get credit if you do not have units, the correct units, along with a numerical answer. Finishing up, C, calculate the maximum height above the ground that the water reaches upon leaving the pipe vertically. In this case, you could apply kinematics and or I think you can do fluid mechanics. Bernoulli should actually still give you the correct values on that, but you can do kinematics or energy. D, calculate the horizontal distance from the pipe that is reached by the water exiting the pipe at 60 degrees from level ground, assuming air resistance is negligible. Definitely not going through that one. That is a projectile motion problem, but something that you should be aware of because that is fair game, definitely on the AP exam or technically my exam, though usually try and keep my exams to be unit focused. But the AP exam may definitely have that, and it's a skill we expect you to have back from Unit 2. All right, so I think this is all the key ideas on continuity equation. Until next time.